June 15, 1944. Ozuki Airfield, Western Honshu, Japan. 0024 hours local time. The air raid alarm shattered the midnight stillness as 24 Kawasaki Ki-45 Toryu heavy fighters of the 4th Sentai scrambled into the darkness. Their target was something the pilots had never encountered, something their commanders assured them would be easy prey. Captain Isamu Kashide, a veteran of operations in China and the Philippines, climbed his twin-engine interceptor into the night sky over Kyushu. Through his cockpit canopy, he could see the searchlight beams stabbing upward, searching for the approaching enemy. Intelligence reports had described the new American bomber as large and ungainly, 4 engines, slow to maneuver, a flying target. What the Japanese pilots climbing above Yawata that night did not know, what none of Imperial Japan's air defense commanders could have imagined, was that the aircraft approaching from China represented the most expensive weapons program in human history, more costly than the atomic bombs it would one day carry. Within 14 months, these bombers would transform from curiosities into instruments of annihilation, their crews working in heated comfort while Japanese interceptor pilots froze and gasped for breath 6 miles above their homeland. The Boeing B-29 Superfortress had arrived, and Japanese air defense doctrine was about to become obsolete. The 19th Air Brigade scrambled its fighters based on radar contacts that had been tracking the approaching formation since before midnight. But the Japanese radar stations confronted an immediate problem. Their equipment could detect the bombers, but could not determine their altitude. This technical limitation would prove catastrophic. The American bombers were not flying at the 18,000 to 22,000 feet that Japanese interceptors expected. They were cruising at 30,000 feet and above, altitudes where the thin atmosphere transformed the physics of aerial combat. Japanese fighter design had evolved to counter threats at conventional altitudes. The Kawasaki Ki-45 Toryu achieved a maximum speed of 335 miles per hour at 19,685 feet with a service ceiling of 32,810 feet. These specifications seemed adequate on paper. In practice, they meant Japanese pilots struggled to reach the same altitude as the B-29s, and even if they succeeded, their aircraft became sluggish and unresponsive in the thin air. What the Japanese military establishment failed to grasp was the fundamental technological advantage the Americans possessed. The B-29 was not merely a larger bomber, it was the first mass-production aircraft with a fully pressurized crew compartment, allowing its 11-man crew to operate in shirt-sleeve conditions at altitudes that reduced enemy fighters to gasping, struggling shadows. The development of this capability traced back to 1938, when Boeing first flew the Model 307 Stratoliner. That aircraft, the first pressurized airliner to enter production, could maintain a cabin altitude of 8,000 feet while cruising at 20,000 feet. It flew above most weather, providing passengers a smoother ride while demonstrating the feasibility of pressurized flight operations. Boeing engineers recognized the military potential immediately. A pressurized bomber could operate above enemy defenses, its crew alert and comfortable, while interceptors struggled and anti-aircraft guns fell short. The Stratoliner employed the wings, tail, and landing gear of the B-17 Flying Fortress, mated to a new circular section fuselage designed to withstand the structural stresses of pressurization. Pan American Airways and Transcontinental and Western Air ordered 9 aircraft, each carrying up to 33 passengers in unprecedented comfort. The technology was proven, the engineering understood. What remained was scaling it to a bomber capable of crossing the Pacific. The Army Air Corps issued specifications for a very heavy bomber in January 1940, demanding 400 miles per hour speed, high altitude capability with a pressurized crew compartment, and 5,000-mile range with a bomb load. These requirements seemed almost impossible to meet simultaneously. Speed demanded streamlined design. High altitude required pressurization. Range demanded fuel capacity that added weight that reduced speed and altitude. Defensive armament demanded turrets that created drag and required crew exposure. Boeing's chief designer, Wellwood Beale, led a team that solved these contradictions through radical innovation. Rather than exposed gun positions, they designed remote-controlled turrets operated from inside the pressurized hull. Rather than a conventional supercharger, they specified turbo superchargers that maintained engine power at extreme altitude. Rather than a standard fuselage, they created three separate pressurized compartments connected by a tunnel. Boeing responded with a design that would consume $3 billion in development and production. Adjusted for inflation to modern values, this represented over $50 billion invested in a single weapon system. The sum exceeded the $1.9 billion spent on the Manhattan Project by more than 50%, making the B-29 program the most expensive undertaking of the entire war. General Henry Hap Arnold, commanding the Army Air Forces, called it the $3 billion gamble. The gamble extended beyond money. In May 1941, Boeing received an initial production order for 14 service test aircraft and 250 production bombers before the first prototype had even flown. This commitment increased to 500 aircraft by January 1942. The Army was ordering thousands of aircraft based on paper specifications, trusting that Boeing could solve problems that had never been solved before. The first XB-29 prototype flew on September 21, 1942. It incorporated technologies that pushed the boundaries of contemporary aviation. 4 Wright R-3350, duplex, Cyclone, 18-cylinder radial engines, each producing 2,200 horsepower at takeoff, drove the massive aircraft through the thin air at altitude. These were among the most powerful aircraft engines in the world, twin-row radials with 18 cylinders arranged in 2 banks of 9. Turbo superchargers maintained engine performance above 30,000 feet, where normally aspirated power plants would gasp for oxygen just as human lungs would. These devices used exhaust gases to spin turbine wheels that compressed incoming air before it reached the carburetor. The system was complex and maintenance-intensive, but it allowed the R-3350 to maintain rated power output at altitudes that would starve conventional engines. The second prototype, armed with a Sperry defensive armament system using remote-controlled gun turrets sighted by periscopes, first flew on December 30, 1942. This flight was terminated due to a serious engine fire, foreshadowing problems that would plague the B-29 throughout its service. The R-3350 engines were prone to overheating, their magnesium crankcases feeding fires so intense they could burn through wing spars in minutes. Manufacturing the B-29 became a national effort involving 4 main assembly factories. Boeing operated plants in Renton, Washington, and Wichita, Kansas. Bell Aircraft built super fortresses near Atlanta, Georgia. Glenn L. Martin Company produced them at Bellevue, Nebraska. Thousands of subcontractors fed components into this production network. Each aircraft required over 13 tons of aluminum, half a ton of copper, 600,000 rivets, 9.5 miles of wiring, and 2 miles of tubing. But the true revolution lay in the pressurization system. Air Research Manufacturing Company developed an automatic cabin pressure system that used compressed air from the inboard engine superchargers. From sea level to 8,000 feet, the system provided ventilation only. From 8,000 to 30,000 feet, regulators maintained a constant 8,000-foot altitude pressure inside the crew compartments. Above 30,000 feet, cabin pressure increased gradually, reaching 10,000-foot equivalent at 34,000 feet actual altitude. The maximum pressure differential was 6.6 pounds per square inch, enough to maintain comfortable conditions in the stratosphere. This meant that while Japanese pilots climbed into the oxygen-starved stratosphere, their bodies fighting the effects of hypoxia, their controls sluggish in the thin air, American crews worked in heated comfort, no bulky flight suits, no restrictive oxygen masks for normal operations. The forward and center crew compartments were connected by a 30-foot pressurized tunnel running above the bomb bays, allowing crew members to move between stations during flight. Japanese intelligence initially dismissed reports of the new bomber's capabilities. When reconnaissance photographs revealed the B-29's massive size, some analysts assumed the aircraft would be slow and vulnerable, its weight a handicap in combat. They calculated interception strategies based on experience with smaller American bombers like the B-17 and B-24. What they failed to understand was that the B-29 specifications represented a fundamental paradigm shift. In wartime configuration, the aircraft was capable of flight at altitudes up to 31,850 feet at speeds approaching 350 miles per hour, true airspeed. Japanese fighters could barely reach that altitude. Fewer could catch the B-29 if they managed to climb that high. The night of June 15th through 16th, 1944 demonstrated these realities. 68 B-29s departed bases around Chengdu, China, bound for the Imperial Iron and Steel Works at Yawata on Kyushu. This was the first American strategic bombing raid on the Japanese home islands since the Doolittle raid more than 2 years earlier. 47 aircraft bombed the target area, releasing 107 tons of bombs through darkness and smoke. The raiders had been tracked since crossing into occupied China. Radar stations and lookout posts on Jeju-do detected the approaching bombers between 2331 and 0030 local time. The 4th Sentai's Ki-45 interceptors achieved only one confirmed kill that night. Warrant Officer Sadamitsu Kimura shot down B-29 42-6230, the Limber Dragon. All 12 crew members were killed, including Newsweek correspondent William T. Schenkel. The Toryu was slower than the bombers, too lightly armed for decisive damage, and most aircraft lacked radar for effective night interception. Despite initially claiming 8 bombers destroyed and 4 damaged, Japanese commanders quickly determined that only 2 B-29s had been lost to enemy action. This loss ratio was considered entirely too low to defeat sustained attacks on the home islands. Japanese after-action reports revealed the scope of the problem. The new American bomber operated above the effective ceiling of most interceptors. It flew faster than fighters at those extreme altitudes. Its defensive armament was unlike anything Japanese pilots had encountered. The raid demonstrated that Japan had too few air bases and insufficient aircraft available for night operations. The performance of the 131st Anti-Aircraft Regiment during the raid was judged so poor that its commander was transferred to Manchuria. The B-29's General Electric Central Fire Control System represented another technological leap that Japanese intelligence had not anticipated. Rather than traditional manned turrets that exposed gunners to the elements, Boeing engineers designed a remote-controlled system that kept all crew members inside pressurized compartments. The system was so advanced that General Electric had competed against Bendix, Sperry, and Westinghouse for the contract, with Sperry initially winning before GE was selected as backup and eventually became the primary contractor. 5 sighting stations, 1 in the nose, 1 in the tail, and 3 in plexiglass blisters in the central fuselage, controlled 4 power-operated turrets, plus a manned tail position. The upper forward turret mounted 4 50-caliber machine guns. The other 3 remote turrets each carried 2 guns. The tail position initially mounted 2 50-caliber guns and a 20mm cannon, though the cannon was later removed due to reliability and trajectory matching problems. 5 General Electric analog computers, 1 dedicated to each sighting station, calculated firing solutions that compensated for airspeed, gravity, temperature, humidity, and target motion. These were electromechanical devices using electrical relays rather than the gears and levers of purely mechanical computers. They were significantly faster than any previous fire control system and could track targets moving at speeds that would have been impossible for human gunners to calculate. The computers made corrections in 3 main areas. Ballistics calculations accounted for the behavior of the projectile after leaving the muzzle, including gravity drop and air resistance. Lead calculations determined how far ahead of a moving target to aim based on range and target velocity. Parallax corrections compensated for the distance between the gunner's sighting station and the remotely located turrets. A gunner could simply track an approaching fighter, and the computer would calculate the proper lead, adjusting the turrets to place the bullets where the enemy aircraft would be, not where it appeared at that instant. A bomber flying at 250 miles per hour at 30,000 feet would curve a bullet approximately 36 feet due to the aircraft's own motion. A 50 caliber bullet drops almost 14 feet at a range of 800 yards. The computer handled these calculations automatically, allowing gunners to focus on tracking targets rather than mental arithmetic. This system allowed a single gunner to operate multiple turrets simultaneously. The upper gunner, acting as fire control officer, could coordinate defensive fire across the entire aircraft. If an attack came from the front, the bombardier could control both upper and lower forward turrets. If fighters approached from high on the flank, the upper gunner could direct both forward and rear upper turrets at the same target. Each turret mounted two Browning M250 caliber machine guns. The combined firepower of 10 heavy machine guns, all aimed by computerized fire control, created overlapping fields of fire that Japanese pilots had never encountered. Head-on attacks, the standard tactic against American bombers over Europe, became suicidal against the B-29. The closing speeds exceeded 600 miles per hour. A momentary lapse in aim left the fighter exposed to concentrated defensive fire. If you're finding value in these lesser-known stories of American technological triumph, consider subscribing to help us continue uncovering them. The struggle of Japanese interceptor pilots intensified as B-29 operations expanded. In November 1944, the 21st Bomber Command began flying missions from newly captured bases in the Mariana Islands. Saipan, Tinian, and Guam placed Japan's industrial heartland within round-trip range. The first attack from the Marianas struck the Musashino aircraft plant near Tokyo on November 24, 1944. 111 B-29s participated. 125 Japanese fighters scrambled to intercept. Japanese air defense forces scrambled every available type. The Kawasaki Ki 45 Toryu twin-engine fighter had proven inadequate at Yawata. The Kawasaki Ki 61 Hien, Japan's only liquid-cooled fighter in frontline service, could reach the required altitudes, but its temperamental engine caused chronic reliability problems. The Nakajima Ki 44 Shoki, designed specifically as a high-altitude interceptor with an astonishing climb rate reaching 5,000 meters in just over 4 minutes, became the most feared Japanese fighter among B-29 crews. The Kai 44 mounted two 40mm autocannons, the heaviest armament carried by any single-seat fighter opposing the B-29s. These weapons could destroy a bomber with a few hits, but they fired slowly and carried limited ammunition. The closing speeds at high altitude left only seconds for an attack run. A pilot who missed his first pass often could not catch the bomber for another attempt. The Navy contributed the Mitsubishi J-2M Raiden interceptor and the Kawanishi N-1K Shiden, but inter-service rivalry hampered coordination. Army and Navy units used different radio frequencies, different tactical doctrines, different chains of command. The fragmented defense allowed B-29s to exploit gaps between areas of responsibility. The mathematics of interception had become brutal. To reach 30,000 feet from sea level, Japanese fighters required approximately 5.5 to 6 minutes at best climb speed. During that climb, they were slow and vulnerable, consuming precious fuel and ammunition time. When they finally reached altitude, they were traveling at climb speed rather than combat speed, easy targets for the waiting bombers. The B-29, meanwhile, had reached altitude long before crossing into Japanese airspace. Its crews had eaten, checked equipment, and prepared for combat in comfortable conditions. The bomber maintained its speed advantage even at maximum altitude. Japanese fighters that managed to reach the same level found themselves chasing aircraft they could barely catch. The physiological contrast was devastating. At 30,000 feet, atmospheric pressure drops to roughly 1/3 of sea level. Oxygen partial pressure falls proportionally. Without supplemental oxygen, a human at this altitude experiences the onset of hypoxia within seconds. Time of useful consciousness, the period during which a person can still take effective action, drops to approximately 1 minute at 30,000 feet. At 35,000 feet, it falls to 30 seconds or less. Japanese interceptor pilots flew in unpressurized cockpits. They wore oxygen masks, but the equipment was often unreliable. Cold penetrated their flying suits. At 30,000 feet, temperatures routinely reached minus 40 degrees, a point where Celsius and Fahrenheit scales converge. Controls became stiff and unresponsive as lubricants thickened. Pilots reported difficulty maintaining concentration, their minds dulled by marginal oxygen supply and extreme cold. American B-29 crews, by contrast, experienced cabin temperatures maintained by gasoline-operated heaters controlled by automatic thermostats. They wore standard uniforms rather than bulky survival gear. Their minds remained sharp, their reactions quick, their equipment functioning normally. The pressurized environment maintained physiological conditions equivalent to 8,000 feet altitude, well within the range where humans function without impairment. This contrast extended to combat effectiveness. A Japanese pilot struggling with hypoxia and cold, fighting sluggish controls in thin air, faced American gunners working in comfort with computerized fire control. The advantage was not merely technological, it was physiological, psychological, comprehensive. The combat records demonstrated Japanese desperation. From August 1944, pilots began resorting to ramming attacks, a tactic called tayatari, meaning body strike. On August 20th, during a daylight raid on Yawata, Sergeant Shigeo Nobe of the 4th Sentai intentionally flew his Ki-45 into a B-29. The collision destroyed both aircraft and severely damaged another superfortress, which also went down. This single attack killed Nobe and brought down 2 bombers. Japanese commanders recognized that ramming was effective, where conventional interception had failed. On November 7, 1944, the officer commanding the 10th Hiko Shidan made ramming attacks a matter of policy by forming dedicated special attack units. These were not kamikaze in the sense of suicide attacks against ships. They were deliberate ramming units formed because conventional fighter tactics proved nearly impossible at high altitude. The aircraft assigned to these units were stripped of fuselage armament, protective armor, and any equipment not essential to reaching altitude. With reduced weight, the lightened fighters could climb higher and faster. Pilots were expected to ram B-29s and attempt to survive by bailing out after impact. Membership in these units was viewed as a final assignment. The pilots would continue flying ramming missions until death or serious injury ended their service. First Lieutenant Toru Shinomiya led one such unit, the Hagakure Tai of the 244th Hiko Sentai. On December 3, 1944, Shinomiya successfully rammed a B-29 and managed to land his damaged Ki-61 fighter despite losing most of the port outer wing. He and 2 fellow pilots who completed ramming attacks that day became the first recipients of the Bokosho, Japan's equivalent of the Victoria Cross or Medal of Honor, an award newly created by Imperial Edict on December 7, 1944. The creation of this award specifically for ramming attacks illustrated the strategic failure Japanese forces faced. They could not stop the B-29s through conventional means. Their best pilots were sacrificing themselves in desperate collisions because their aircraft could not effectively fight at the altitudes where the Americans operated. By February 1945, the strategic calculus had shifted further against Japan. General Curtis LeMay, commanding the 21st Bomber Command from the Marianas, recognized that Japanese air defenses were weaker than anticipated. High-altitude precision bombing had proven ineffective due to cloud cover and the newly discovered jet stream that carried bombs miles from their targets. LeMay made a radical decision. For the massive incendiary raid on Tokyo planned for March 9th, he ordered his B-29s to attack at night, at low altitude, without most of their defensive armament. The risk seemed enormous. Lower altitude, would bring the bombers within range of fighters and flak. Removing guns would leave them vulnerable. But LeMay understood that Japanese night fighter capability was minimal. Only 4 dedicated night fighter units existed in the entire Japanese Air Force, and only 2 were stationed in the home islands. By attacking at 5,000 to 9,000 feet rather than 30,000, his aircraft could carry far heavier bomb loads. Each B-29 could carry 40 E-46 bomb clusters. Each cluster, exploding at 2,500 feet, would release 38 M69 incendiary bombs in a random pattern. The tactics drew from British experience over Germany. Rather than formation bombing, aircraft would attack individually at night. Rather than armor and ammunition, they would carry fuel and incendiaries. The Office of Strategic Services had produced maps ranking Tokyo's wards by susceptibility to fire, analyzing building density, construction materials, and even pre-war Japanese insurance company risk assessments. 334 B-29s took off from the Marianas on the night of March 9th. 279 reached Tokyo and dropped 1,665 tons of incendiary bombs onto the Shitamachi neighborhood. 14 aircraft were lost to all causes, a rate of about 3%. Japanese air opposition was weak. 74 fighters made only 40 attacks. The anti-aircraft fire was intense over the target, but diminished as the attack progressed. The results exceeded all expectations. 16 square miles of Tokyo burned. 267,000 buildings were destroyed. Estimates of civilian deaths range from 80,000 to over 100,000 in a single night. The raid demonstrated that Japanese defenses could not stop the B-29 at any altitude when the Americans chose to accept the risk of lower approaches. Yet even at low altitude, the B-29 retained its technological advantages. The pressurized compartment still protected crews from smoke and fumes. The computerized fire control still functioned, and tail gunners retained their weapons for defense against any fighters that managed to intercept. The numbers accumulated into overwhelming American dominance. By June 1945, 444 B-29s attacked Osaka in a single raid. Not one Japanese fighter rose to oppose them. The fighter defense of the home islands had effectively collapsed. The combination of pilot losses, aircraft attrition, fuel shortages, and sheer exhaustion had broken Japanese air power. Statistics from the 20th Air Force tell the story. From November 24, 1944 to August 14, 1945, 447 B-29s were lost from Marianas-based operations. Of these, only 147 were destroyed by flak and fighters combined. 74 were lost to fighters alone, 54 to anti-aircraft artillery, and 19 to a combination of both. Japanese fighters accounted for just 13% of all battle damage sustained by B-29s over the target. 267 aircraft were lost to engine fires, mechanical failures, and other operational causes. The B-29 gunners reported 11,206 fighter attacks during the war. They claimed 914 Japanese aircraft destroyed, 456 probably destroyed, and 770 damaged. Post-war analysis suggested actual Japanese losses were roughly one-third of claimed destroyed totals, but even the reduced figures represented a devastating attrition of Japanese fighter strength. The grim reality was that American crews faced greater danger from their own aircraft than from Japanese defenses. The Wright R-3350 engines were notoriously unreliable, prone to overheating and fires that could destroy an aircraft in minutes. Crew members joked darkly that they were being killed more by Curtiss Wright, the engine manufacturer, than by the Japanese. Nearly 150,000 man-hours were required to build each early B-29. Ground crews worked constantly to keep the temperamental aircraft flying. Yet even with these losses, the B-29 fleet grew faster than Japan could shoot it down. American factories produced nearly 4,000 superfortresses by war's end. Boeing's Wichita plant alone delivered hundreds of aircraft. Each cost approximately $639,000, over double the cost of a B-17. The unit cost of the three prototypes exceeded $3.3 million each, but cost was irrelevant when national survival depended on the outcome. Japanese intelligence reports captured after the war revealed the growing desperation of their assessments. The new American bomber operated above effective interception altitude. Its defensive firepower was unprecedented. Its production rate exceeded all projections. Each damaged fighter was difficult to replace. Each lost pilot was irreplaceable. The ramming tactic, once seen as an act of supreme courage, became an admission of defeat. By war's end, ramming attacks had destroyed 9 B-29s and damaged 13 more at a cost of 21 Japanese fighters and their pilots. This exchange ratio, roughly 2-to-1 in Japan's favor, might seem acceptable until one considered that America lost 9 bombers out of tens of thousands of sorties. Japan lost 21 pilots it could never replace. In the final months, Japanese commanders confronted impossible mathematics. The 21st Bomber Command was conducting raids with 500, 600, even 1,000 aircraft. Japanese fighter production had collapsed under the weight of American bombing. Fuel supplies had dwindled to the point where training flights were curtailed. New pilots arrived at combat units with fewer than 100 hours total flight time, insufficient to master the demanding interception profiles required against B-29s. Major General Minoru Genda, the tactical genius who had planned the Pearl Harbor attack, assessed the situation bluntly. The B-29 represented a technological generation Japan could not match. Its pressurization, its fire control, its engines, its sheer scale of production, all exceeded Japanese capabilities. The home islands were defenseless. The United States Strategic Bombing Survey, conducted after Japan's surrender, documented the comprehensive failure of Japanese air defense. Prisoners were unanimous in their grudging admiration for American air power. Allied artillery and bombing caused Japanese forces to feel insecure along the entire front. The demoralizing effect of sustained aerial attack was characterized by helplessness, panic, and confusion in the ranks. Japanese pilots who survived the war provided testimony confirming the futility of conventional interception. The Ki-45 Toryu had proven too slow, too lightly armed, and lacking in high-altitude performance. The Ki-44 Shoki could reach the bombers but carried insufficient ammunition for sustained combat. The Ki-61 Heian suffered constant engine failures. The Navy's J-2M Raiden showed promise but arrived too late and in too few numbers. When the atomic bombs fell on Hiroshima and Nagasaki in August 1945, they were delivered by modified B-29s flying at altitudes where Japanese fighters could barely operate. The Enola Gay approached Hiroshima at 31,600 feet. Bockscar reached Nagasaki despite having to make 3 bombing runs, while Japanese defenses proved unable to mount effective opposition. These silverplate modified aircraft had been stripped of most defensive armament to save weight for the massive bombs, yet they completed their missions without effective interference. Captured Japanese documents revealed the evolution of assessments regarding the B-29. In June 1944, analysts had described it as large and ungainly, potentially vulnerable to aggressive interception. By December 1944, reports acknowledged exceptional high-altitude performance and extreme structural strength. By March 1945, evaluations labeled it the dominant bomber of the war, with a combination of firepower, durability, and performance unmatched by any other type. The B-29 program represented American industrial philosophy perfected. $3 billion invested in an aircraft that could fly higher, faster, and more comfortably than anything in the Japanese arsenal. Pressurization technology that traced back to commercial airliners of the 1930s. Computerized fire control that substituted engineering for individual marksmanship. Production rates that buried enemy resistance under an avalanche of aluminum. The Boeing Superfortress carried the war to Japan in ways that no other aircraft could have matched. It burned 67 Japanese cities to the ground. It dropped the weapons that ended the Pacific War. It proved that industrial mobilization and technological innovation could overcome geographic distance and enemy determination. The pressurized cabin was the key that unlocked everything else. Without it, crews could not have operated effectively at the altitudes where the B-29 was invulnerable. Without it, missions lasting 16 hours or more would have exhausted crews beyond usefulness. Without it, the B-29 would have been just another bomber, vulnerable to the same fighters that had savaged earlier aircraft. But with pressurization, American crews worked in conditions comparable to ground-level offices. They ate, rested, and monitored equipment in heated comfort. They arrived over targets alert and ready, while Japanese interceptors struggled against hypoxia and cold. The technological gap was insurmountable. The Soviet Union recognized this when 4 B-29s made emergency landings in Soviet territory during 1944 and 45. Rather than return the aircraft, Stalin ordered Andrei Tupolev to copy the B-29 exactly. The resulting Tu-4 moved Soviet aviation technology to a new level, providing pressurized cabins, turbo-supercharged engines, and computerized fire control that the Soviets had not previously possessed. The B-29 had been so advanced that America's future Cold War rival devoted years to duplicating it exactly. June 15, 1944. Captain Isamu Kashide and the pilots of the 4th Sentai had scrambled against an enemy they believed would be easy prey. 14 months later, not one Japanese fighter rose to meet 444 B-29s over Osaka. The bomber Japan could never reach had systematically destroyed Japanese air power, burned Japanese cities to the ground, and carried the weapons that ended the war. The Japanese had prepared defenses against bombers flying at 20,000 feet. The Americans arrived at 40,000. Japanese pilots froze and gasped in unpressurized cockpits. American crews worked in heated comfort, protected by technology their enemies could not match. In 1944, Japanese interceptor pilots died ramming B-29s because conventional interception had become impossible. By 1945, there were too few pilots left to ram anything. The $3 billion gamble had paid off in the total defeat of Japanese air defense. The sky belonged to America, and the pressurized cabins of the B-29 had made it so.